Hello everyone. In this video, I'm going to discuss the principles on rotated vessels and their relative equilibrium for rotational motion. So the principles are important before watching the videos on the sample problems because the only way to understand the example problems will be to master the principles first. So here I'll discuss the formulas and principles on parabolas and paraboloids. So if this is now the resulting uh, parabolic surface when the cylindrical tank is rotated about its vertical axis through an angular rotation of omega radians per second or omega revolutions per minute, then the volume of this air paraboloid is equal to the volume of liquid under that air paraboloid but inside the right circular cylinder. In other words, the volume of the paraboloid is one-half the volume of the circumscribing cylinder. So that is volume equals, or when the tank is stopped, when the rotation is stopped, then the liquid will be in equilibrium and it will have the surface here which is half the depth. So that is the volume of paraboloid with one base is pi over 2 r square h, big H. So if you're going to analyze, this volume is half the volume of the circumscribing cylinder. Now, this formula can be derived from integral calculus or known from solid geometry. Now, if we have a paraboloid such that the original depth is greater than half the height of the tank, then the same principle applies. When the tank is brought to rest, then the liquid level will have this horizontal surface here, which will divide the original height h into halves. So that's h over 2, that's h over 2. Again, the volume of this air paraboloid with one base is equal to pi over 2. Imagine this right circular cylinder here, up to this vortex here. The volume of the air paraboloid is pi over 2 radius square, big R square times small h this time because the height is small h. And aside from this property, you should also know the squared property of parabola. That is, so because this is a parabola, that is y as to x square, vertical as to square of horizontal equals vertical small h as to the square of big radius. So squared property of parabola, y as to x square equals small h as to big R square. So I hope that you already know that. So still on formulas and principles on parabolas and paraboloids. So let's have the situation here. This time we have an open cylindrical tank, and because of high speed of rotation, the parabola extends below the bottom center, and we have here an imaginary paraboloid, and the bottom is exposed partially. So these are the important concepts, formulas that you should be able to set up. So we have a paraboloid of revolution with two bases here. The volume with paraboloid of revolution with two bases is pi over 2 quantity r1 square plus r sub 2 square times big H. So that's the volume of a paraboloid with two bases. And that is represented by this volume of air which remains inside the cylindrical tank. Now, another way of computing this volume of air inside the parent right circular cylinder is it is equal to volume of the big paraboloid with single base R1 or single radius R1 minus the volume of this small paraboloid which extends outside the parent cylinder. So that is equal to pi over 2 R1 square times quantity H plus Y sub 2 minus pi over 2 R2 square times Y sub 2. So that's the other way of computing this volume of air represented by a paraboloid of revolution with two bases. So the results, these two results will be the same, but I just enclose this because this is the direct formula also. So for the liquid part, the analysis is it is equal to volume of this right circular cylinder full capacity, then you have to subtract the volume of air inside, which is equal to this volume here. So that's it for that case. Now, when the tank is brought to rest, naturally the liquid contents inside will have its surface horizontal, which is represented by this. Now the question is the principle before that when the liquid surface is horizontal as this, will the height above this horizontal surface to the top still equal to the height below? In other words, if the total height is h plus y2, will this still be h plus y2 over 2? H plus y2 over 2. Quantity h plus y2 over 2. Now, the answer is it's no longer true because of this portion of the paraboloid which extends beyond the right circular cylinder. So this principle is only true when the paraboloid that forms is within the parent right circular cylinder. If it goes beyond, below, or above, then this principle does not apply anymore. So that's not true. That's not true anymore. So I hope you got it and remember that principle. Now the squared property of parabola applicable for this situation would now be y2 as to r2 square equals y2 plus h as to r1 square. So again, y2 as to r2 square equals y2 plus big H as to r1 square. So that would be the square property of parabola applicable for this case. Now, let's have a situation where we have a closed top tank and these are the details. So if this is the resulting paraboloid, imaginary paraboloid of revolution because of high speed rotation, then these are the details, the height of the paraboloid inside the cylinder from the vortex to the top to the closed top is y sub 2 and the overall height is denoted by small h. Then still this does not apply anymore. So in other words, this horizontal surface will not divide the height into halves because the paraboloid of revolution extends outside the parent right circular cylinder. So what are the information that we can establish here? So these are the details. So the squared property of parabola would then be y2 as to r2 square equals h as to r square. That would be the squared property of parabola that you can set up. Y sub 2 as to r2 square equals h as to r square. Now for the volume of air inside the parent uh, paraboloid, then you have to equate it with the original volume of air because take note, no air can escape with this closed tank. So the idea then is we equate the volume of this paraboloid inside the parent right circular cylinder, which represents the final volume of air, to the initial volume of air. So the final volume of air represented by this paraboloid of single base is pi over 2 r sub 2 squared times y2. Then equate that to the original volume of air, which is pi r squared times k. So that's it for this situation here. So I hope you got it and apply it to some problems there. So let's continue with some other situations for closed tanks. Now, if the imaginary surface, parabolic surface, is such that the vortex exactly forms on the bottom center of the cylindrical tank, so same condition as before, we have the depth greater than half of the height and this empty depth as K. So this volume of air is the same as the original volume of air. So since there's only one base, and we'll denote the following: the overall height. By the way, the height of the paraboloid when the vortex exactly forms at the bottom center is, I denoted it with h sub v, and we'll derive that formula later. And this is r sub 2, and that's big R also, same as this. So therefore, the volume of air represented by a single paraboloid with radius r sub 2 and height big H is equal to pi over 2 r2 square times big H, and it should be equated to the original volume of air, which is pi r square times K. Then another way is this volume of air inside is also equal to volume of big paraboloid minus volume of this parabolic segment with two bases. So volume of air is also pi over 2 r square times hv minus this volume of imaginary parabolic segment with two bases, pi over 2 times quantity r square plus r2 square times height h sub v minus h, because this is h sub v and the overall height is big H, so this is h sub v minus h. Notice that if you're going to simplify this equation, it will go back to this pi r2 square 8 big H over 2. So that's it. Then for the squared property of parabola in this figure here, so we have big H as to r2 square equals h sub v as to r square. Again, vertical hv, this is hv, the radius is r2 square, is r2. So big H as to r2 square equals h sub v as to r square. So that's the squared property of parabola that we can establish. Now for this same closed cylindrical tank, and we have a situation where the imaginary parabolic surface will extend beyond the bottom, so we have an exposed bottom here because of very high value of rotation, angular speed. So same condition, and we have here big R, R sub 2, R sub 1, then Y1. So the volume of air, which is represented by this parabolic segment with two bases, or paraboloid of revolution with two bases, should be equated to the original volume of air, because no air can escape because the tank is closed. So therefore, pi over 2 times quantity r1 square plus r2 square times big H, that's the volume of paraboloid with two bases, is equated to pi r square, because the radius of the cylinder is big R, times K. So that's the equation that you can establish. Equate final volume of air represented by this paraboloid of revolution with two bases, pi over 2 quantity r1 square plus r sub 2 square times big H is equated to the original volume of air, which is pi r square times K. But do not memorize, just memorize the formula for volume of paraboloid with a single base or two bases. Then the squared property of parabola that we can establish here is y1 as to r1 square equals y1 plus big H as to r2 square equals small h as to r square. So again, y1 as to r1 square you set up the squared property of parabola equals y1 plus big H as to r2 square equals small h as to r square. That's it for this part. So let's now have the principles on rotated vessels. So first we have the expressions for normal acceleration. So this is the resulting paraboloid, and the rotation is such that this is the resulting surface, which we're going to define as we continue. So this is the top view of this circular path at the intersection with the walls of the tank, and the radius is big R, and this is called the tangential velocity V. Then we have a point here on the resulting surface, which is at rest. So take note that it is only the tank that is rotated. The contents inside remain at rest. So normal acceleration, there are three expressions for normal acceleration. One is the tangential velocity square over radius, big R. It is also equal to omega square r, and it is also the product of the angular velocity and the tangential velocity. So therefore, the expression for tangential velocity v is also omega times radius. So that's why here, if you break omega square into omega r, and replace omega r by v, so that's why we have another expression for normal acceleration. Now, because the tank is the vessel that is rotated, but the contents inside assume this shape, the liquid particles, the liquid contents, the particles inside remain at rest. So therefore, if we have a point on the surface, resulting surface here, it's assumed by this after the tank is being rotated, so everything here, all particles here remain at rest, including this particle here. So we analyze this particle here. We have its weight, and since there is normal acceleration towards the center, there is reverse effective force, which is equal to mass times normal acceleration. And because its radius or distance from the axis of rotation is x, then that reverse effective force is equal to W over G, mass, times omega square x, because the radius is x. And because this is at rest, there should be a force that will make it in equilibrium, and we will denote that by normal force due to the other particles that under this or surrounding this particle here. So the angle between the vertical and the normal is also theta. So if we draw the first triangle, we have the weight, then horizontal omega W over G times omega square x, then the normal, and this angle here is theta. So therefore, from this figure, tangent of theta equals W over G omega square x divided by W. So cancelling out W, tangent theta is equal to omega square x over G. Therefore, we have defined the slope of the tangent to that point on the surface of this surface here of equal pressure. So tangent theta, which is the slope, is omega square x over G, where omega here is in radians per second. Then for the maximum slope, it occurs at the surface on the periphery of the wall. So this is the tangent, and this angle here is theta max. So all you have to do is replace x by big R, because at that point x is equal to R. So tangent theta max is equal to omega square big R over G. That's the expression for the maximum slope at the surface at the resulting surface of equal pressure. By the way, the all points here on the surface will have equal pressure. So if it is exposed to the atmosphere, then all points here will have zero pressure. So since tangent theta from calculus is also the slope or dy dx, and it is equal to omega square x over g from this slope here. So dy equals omega square x over g times dx. So integrating this, omega square over g constant. So we have omega square x square over 2g plus constant of integration. We will call that by small c. But when from the figure, the vortex forms on the axis of rotation, and it is at the lowest point. So when x is 0, y is also 0. So therefore the constant is 0. And therefore c is 0. So when x is r here, big R, y is equal to small h. So therefore, into this equation here, y equals omega square x square over 2g, because c is 0. This is the equation of this surface, which is a second degree curve, and because this is constant, this is a parabola. And because this is a solid, this is a paraboloid of revolution, but the plane section is a parabola. So that's it. So therefore, we have shown that this resulting surface is a parabola. So when x is r, y is h. So therefore, the formula for h, distance from vortex to the point where the radius is r, is omega square big R square over 2g, where omega again is in radians per second. And since omega times r is tangential velocity, this is also v squared over 2g, or velocity head. In in fundamentals of fluid flow, we will define this one form of energy later. So since in most cases the given angular speed is expressed in revolutions per minute, so we will derive a direct formula for h, where the angular speed is in revolutions per minute. So we replace this angular speed here in radians per second to omega in revolutions per minute by multiplying pi over 30 as a factor to make that in radians per second. Then simplifying, h will now be 0.000.0005589 omega square r square, where omega is in revolutions per minute in this case. So that's the direct formula for the height of the paraboloid formed when the given angular speed is expressed in revolutions per minute. So that's it. So here I'll discuss cases of drawing the resulting liquid surfaces of equal pressure for open tanks. So if the tank is rotated slowly, that the parabolic surface of equal pressure will just be below the top rim as shown in the figure. So no liquid is spilled for this case, and this H1 here will be, again by principle, will be divided by this horizontal line. So that's H1 over 2, H1 over 2. So formula for H1, omega square big R square over 2G, or 0.0005589 omega square R square for omega in revolutions per minute. Then that's for H1, which is less than twice of this 2K, twice of this K here, empty depth. So take note that the depth is greater than half the height of the tank. Then this is the situation when the parabolic surface just touches the top rim. That's the maximum. This is the surface with maximum height allowed without spilling any liquid. Beyond that, then certain amount of liquid will be spilled. So this is the parabolic surface of height equal to 2K by principle because no liquid is spilled yet, such that we can compute the maximum angular speed without spilling any liquid. So the height is denoted by h2 and this distance is also k. So that's why h2 is equal to 2k. No spillage for that case. Then when the tank is rotated such that its surface or height of the imaginary parabolic surface will be greater than 2k but less than h, then we will call the height as h sub 3. So certain amount will now be spilled and that is h sub 3. Then another case is when the vortex exactly forms on the bottom. So for this situation here, 2k is less than h sub 3 but h sub 3 is less than big H. So certain amount is spilled for that case. And another case is when the tank is rotated such that the vortex exactly forms on the bottom center or barely exposed. The bottom center is barely exposed or zero pressure if it is open. Then the height is denoted by h sub v for that case. Now for this case, if we are asked to compute for the volume that is spilled, remember that the volume of this paraboloid is equal to, with single base, is 1/2 the volume of the circumscribing cylinder. Therefore, the volume that is spilled is volume of paraboloid air minus original volume of air. So that is pi over 2 big R square times big H, that's the volume of the paraboloid represented by air, minus original volume of air, which is pi R square K. Another way of computing that is, since the final surface will be settling half of the height of the tank, then it is equal to original volume of liquid pi R square D minus half the capacity pi over 2 R square H. So volume spilled is also pi R square D, original volume, minus half the capacity, because the volume of under the paraboloid inside the cylinder is also the same, pi over 2 R square H, R square big H. Then when the angular rotation is such that the bottom is exposed, so certain volume is spilled, certain amount of liquid is spilled, then we will denote this as the case where H4 is greater than big H and some other information. So this is now exposed. So we have Y4 and this radius of the exposed circle is R sub 4. Then we have air here, which is represented by a parabolic segment with two bases. So volume spilled would be volume of the tank minus volume of air, represented by these two uh, paraboloid with two bases. So original volume of tank is pi big R square times big H volume of cylinder minus volume of air final, represented by this paraboloid with two bases, which is pi over 2 quantity big R square plus R4 square times big H. So that's the volume spilled. Now for the case of H3, volume spilled is volume of air final minus volume of air original. So volume of air final is single base paraboloid pi R square times H3, pi over 2 R square times H3 minus volume of air original pi R square K, represented by this right circular cylinder. So that's it, that equation that we can establish for this case. So in these cases, let's continue, this time for closed cylinders or rotated vessels, full closed tanks. So if the initial pressure at the top is 0, then this will be the imaginary parabolic surface. It passes through 0 pressure. So all points on this surface here will have 0 pressure also. So this is the resulting height, and h is omega square big R square over 2g in radians per second, omega in radians per second, v square over r, or 0.0005589 omega square R square if the given angular speed is in revolutions per minute. Then we call these surfaces of equal pressure, and the pressure is equal to 0 because initially the pressure at the top is 0. Then if we draw a surface parallel to that, then this is called surface of equal pressure, and the pressure is gamma times h1 because the vertical distance between any points is h1 as shown in the figure. So Pmax occurs at the periphery on the bottom, and it is equal to gamma of this liquid here times quantity small h plus big H, and it occurs at the periphery of the bottom. Then the pressure at the bottom center is just gamma times big H. So for this situation here where there is initial pressure PO, so we convert PO into pressure head first as shown. Then this is now this vertical distance is PO over gamma. So PO over gamma. Then all points here on this horizontal imaginary surface will have 0 pressure. So when the tank is rotated, then the vortex will be on this 0 pressure here, and it will assume that parabolic surface there of height small h, again given by this formula here, and the maximum, we call that surfaces of equal pressure, this time 0 because initially the pressure here is 0. So therefore Pmax occurs at the periphery of the bottom, and it is equal to gamma times quantity h plus p over gamma plus big H. And the pressure at the bottom center is equal to gamma times quantity p over gamma plus big H only. So that's it for this portion of the slide. So here we have rotated closed vessel, partially full with or without pressure in the airspace. So this is the situation, the depth d, empty depth k, and the overall height h. So if it is rotated slowly, that the imaginary surface will not reach the top closed trim, then the height is denoted by h1, and remember this is h1 over 2, this is also h1 over 2. So h1 here is less than 2k. Then this is the situation where the surface just touches the top rim here. Then that's the case where H2 is equal to 2K. And next is when, that's why it's K and this is K also. When the rotation is greater than this situation here, that the vortex is below but above the bottom center and crosses the top close portion cover. So this is the situation. We'll denote the height as h3, which is less than hv, because hv is the height of the paraboloid when the vortex exactly forms on the bottom center. So the imaginary surface crosses the top cover with radius r3, and its height is denoted by y3. So therefore, since no the volume of air here represented by this parabolic segment paraboloid with one base is equal to the original volume of air, so for volume we can establish pi over 2 r3 squared times y3 is equal to original volume of air, which is pi r squared times k. So that's it. Then since by squared property of parabola, y3 as to r3 squared equals h3 as to r squared. So from this equation here, r3 squared after canceling out pi is 2r squared k over y3. So y3 over 2r squared k over y3 equals h3 over r squared. So canceling out r squared, then we can establish the formula for y3, square root of 2k h sub 3. So take note that h sub 3 can be determined if omega is known. So that's the formula, but actually you can derive this by your own, applying the principle that volume of air final is equal to volume of air initial, and by squared property of parabola you can establish that. There's no need to memorize that also. Then when the rotation is such that the vortex exactly forms on the bottom center, the height is denoted by h sub v, and we will derive the formula for h sub v for this closed tank here. So again, the volume of air inside the cylinder remains same as the volume of air original. So since there is only one base and the radius is denoted by r sub v for that case, so the volume of air inside the tank is pi over 2 rv squared times big H, and it is equated to pi r squared times k, the original volume of air. Now, establishing rv squared, it is equal to 2 r squared k after canceling out pi over big H. So rv squared is 2 r big R squared k over big H. Then by squared property of parabola, h as to rv squared equals hv as to r squared. So again, hv as to r squared equals big H as to rv squared. The height is big H, the radius is rv squared. So rv squared is big H r squared over h sub v. So replacing this rv squared from here, 2r squared k over big H equals big H r squared over h sub v, canceling out big R squared, then we can now have the formula for hv given by big H squared over 2k. That's a formula for h sub v for this closed tank here, where the depth is greater than half the height of the tank. Then when the rotation is such that the height is greater than hv, that the imaginary parabolic segment exposes the bottom and it extends like this one, and these are the other dimensions. So we have h4 greater than h sub v, then call that y4. This radius is r sub 4, call that r sub 5, and same principle applies. This time this is air final inside the tank, which is the same as the original volume of air. So the volume of air is represented by a paraboloid of revolution with two bases, and we know already the formula for that volume: pi over 2 quantity r4 square plus r5 square times big H, then equated to pi r square times k. So pi over 2 r4 square plus r sub 5 square times big H, volume of paraboloid of revolution with two bases, with radii r4 and r5, and distance between them vertically big H, and equated to original volume of air, which is pi r square k. Then, because there are two unknowns, r4 square and r5 square, by squared property of parabola, y4 as to r4 square equals y4 plus big H as to r5 square equals h4 as to big R square. Then from here, r4 square is in terms of y4 and r5 square is also in terms of y4. Then solving these two equations simultaneously will lead to simple equation, not complicated equations. So that's it for these situations here. Finally, for situations like YouTube's, so if the rotation is about the axis of symmetry of the tube, and assuming the legs are of equal diameter or size, then these are the possible surface. So call that big H. So this is the situation when rotated to such speed that the height is less than big H. Small h is less than big H, where h is omega square big R square over 2g, or 0.0005589 omega square R square, depending on the given angular speed. This is the situation when small h is equal to big H, and this is the situation when small h is greater than big H. So for this situation, the pressure at points somewhere here will be negative, because this imaginary surface is a surface of equal pressure, and it is zero because the legs are open to the atmosphere, so zero pressure. For this situation where the axis of rotation is through one leg, so remember the principle that the vortex always forms on the axis of rotation and at the lowest point. So initially zero pressure, horizontal, and that's big H. So these are the possible scenario. So one will drop, this is the vortex, and the other will rise at the same amount if they have the same size. So this is equal to 2y, h is equal to 2y, and this is the imaginary parabolic surface. This is the vortex. For when the angular speed is increased, this will be the resulting surface, and when increased further, then there will be a possibility that the liquid will start to spill on the other opening. So this is for this situation, h is omega square r square over 2g, v square over r, depending on the given, or the other way around, 0.0005589 omega square r square for omega in revolutions per minute. So in the situations here, all you have to do is replace big R by 2R, because this is 2R. And same is true with this formula here, replace big R by 2R. Then for this situation where the axis of rotation is not through the center, so we have R1 and R2, distances R1 and R2. So this will be the possible surface. So take note that this is h1 and we have h2. So the vertical distance between the ends of the surface can be established. So in general, this distance is omega square over 2g, quantity r2 square minus r1 square. Why omega square over 2g, quantity r2 square minus r1 square? Because from the vortex to that highest point, that's omega square over 2g r2 square, because the radius is r2. And from the vortex to this lower end left, it is omega square over 2g times r1 square. Therefore, the vertical distance between these ends is simply omega square over 2g quantity r2 square minus r1 square. Then lastly, for closed pipes, and assuming the pipe is plug and or cap and there's no pressure initially, if there is pressure, you have to convert it into pressure head first to locate surface of zero pressure, which is horizontal, and same principle applies. So the length of the pipe is L. If in the first case the pipe is rotated about the center, then the vortex forms here because the pressure here is zero, and it will assume that shape, which is parabolic, and the height h1 is omega square over 2g times L over 2 quantity square, because that's L over 2 and that's L over 2. The radius is L over 2. Then when the axis of rotation is through the vertical axis of rotation is through the plug or cup, because the pressure here is zero, so the vortex forms here and it will form that height imaginary surface like that one, and the height is denoted by h sub 2, and h sub 2 is omega square over 2g L square, because the distance or the radius is L. Finally, if the axis of rotation is somewhere here and this distance is big R, then the surface still passes through this zero pressure at the cap, then the vortex is below that cap there. So there is this height here and there is also this height here from the vortex. So therefore, that the net height, which I call h3, from that point to the horizontal axis of the pipe is omega square over 2g times quantity L plus R quantity square, because from this vortex to that end is L plus R, then minus this height here, which is omega square over 2g times R square. So that's why the formula for the net height H3 is omega square over 2g quantity L plus R square minus small r minus big R square. So that's it for this situation. I hope that you're able to follow the principles.